So I will talk today about building quantum machines using neutral atom arrays, and with particular focus on kind of error detection and error correction, kind of leading eventually, hopefully, for fault-tolerant operation. So, but just to start, since it's the first kind of talk in the school about a hardware, building a hardware systems. So this is a part of the broad effort, which one can view as a kind of quest to control quantum world. And in this effort, what we do, we isolate and control some simple quantum objects, like individual electrons, atoms, ions, superconducting qubits, and then try to basically use them as ingredients to build more and more complex systems from them. And with the systems, we of course would like to kind of explore new physics, and usually this involves creating and probing new entangled states of matter, but also we of course would like to eventually use them for new applications and things like quantum information processing, communications, and metrology. And of course, all of you guys are in some way connected to the field. You don't need to tell me that it's a super exciting field, but I think it's also important to step back and kind of recognize the challenges that this field is facing. And actually there are two of them. There are two big outstanding questions in this field which are not really answered up to now. And one is, the question is how we can build truly large scale quantum systems and make them, execute, a lot of operations without errors. I mean, this is ultimately centrally related to the topic of this school, and because basically correcting errors and kind of figuring out how to reduce errors is absolutely central goal in this task. And it's actually, this is really, it's kind of very foundational. And the second question is, of course, once you have these systems, how can you use them to basically do something useful, right? And this is connected to the second issue of kind of useful quantum advantage. And the state where the field is, sometimes I call it like ultimate quantum rivalry. So you could now say, oh, what is it? It's competition between different platforms, or maybe between different, even countries now. But actually, it's much more fundamental. It's a competition between two contradictory forces of nature. And one is a kind of controllability, and one is a scalability. And these two forces are at play in many areas of, human activity. And, for example, like if you have a big organization, composed from smart, PhDs in quantum, science and engineering, is by definition will be very hard to control, But in quantum mechanics, this kind of contradiction is kind of central. And, and like, okay, you all know about this, but, just to kind of make this point very clear. So all objects around us are made fundamentally from quantum particles. But, at the same time, like there is absolutely nothing quantum about this table or about these chairs on which you are sitting, right? Because, and the issue is, usually once you have a quantum system which is, large enough, has a lot of degrees of freedom, it kind of completely loses its quantum character. And what we are trying to do when we try to build quantum computers is to really solve this problem somehow, right? So we want to have a system which is large enough, has a lot of qubits, but yet we could really put it in its superposition and maintain its superposition through the computation. And that's a key challenge, which we are facing. But every challenge is an opportunity, and for this reason, it's actually a very exciting field. So there is now a current frontier involves really trying to use these systems which now have hundreds of qubits, to kind of experiment them and learn how to build bigger and better systems. But also, they are now big enough, these systems, that one can really start addressing, this application challenge, really run some algorithms and you see, to what extent, one could really solve problems that classical computers cannot solve. And so basically, we're at the point, I think I like to call it kind of an era of quantum discovery or age of quantum discovery, where we can really, by experimenting with real hardware, we can really make progress, meaningful progress along both of these directions, So that's kind of a high-level preamble. So with that in mind, I will kind of specifically introduce the focus on this challenge, which is this school about, and this is this quantum error correction. And basically, as the first lecture already kind of indicated, so the errors in basically state-of-the-art quantum computers across different platforms now is at a level of like percent or maybe 1/10 of the percent. But eventually, we'll need these errors to be way smaller, like 10 to the minus 10. And historically, when first ideas of quantum computers were seriously discussed, some people, like some really, very smart people, were really doubting whether this one can ever build, useful large-scale quantum computers for that exactly reason. And they basically argued, look, all objects around us are classical. That's fundamentally, connected to that. Moreover, if you start thinking about quantum error correction, the challenge is that if you, for example, use redundancy, like classical computers, you cannot, in quantum mechanics, you cannot make copies. There is no cloning theorem. Moreover, to check for errors, you need to measure this state, right? And usually when you measure a state in quantum mechanics, you collapse it, right? So it was basically early on, was not even clear that quantum error correction can ever be basically, realized, And it was actually remarkable that, theoretically, people showed starting like 30 years ago, started showing that error correction is possible, at least quantum error correction is possible, kind of even in principle. And the fundamental idea is to delocalize quantum information. So basically in quantum error correction, all quantum error correcting codes, what they do is they prepare special entangled states, so use entanglement to encode quantum information. And this kind of non-local quantum information, basically, if you store it correctly, you can then use this stabilizer measurement, which we heard about in this morning, to try to detect if local errors have occurred. And basically, by being delocalized, this kind of so-called logical degree of freedom is hard to manipulate accidentally. But of course, for that same reason, it's actually hard to manipulate it deterministically. All of a sudden, you have to have a lot of redundancy, you have to have a lot of qubits, and you have to also figure out how to do quantum operations, which actually you have to do in a way which is sort of, protected, which is, quite non-trivial, and these all kind of, adds to the challenge. So at the end of the last lecture, so the idea of like surface of toric code was introduced, and this surface of toric code is an example of something which is called CSS code, which is basically a code. The CSS codes, they are quantum error correction codes, which can be built from product of two classical codes. One which corrects bit flip information, and another one which corrects phase information. And in fact, this can be seen on this kind of, on this surface code, basically, just to remind you, in the surface code, what you do is you have qubits which are, stored on this kind of regular lattice. And then you usually use ancillary qubits to measure these check operators, these Z checks, a product of Z operators kind of around the edge, around the vertex, and X checks, a product of X operators around this, blockade. And so what happens in this case is that, basically, if your system doesn't have errors, then all stabilizers should be +1. But if one error occurs, then, for example, if one qubit flips, then if you measure these checks, you'll see, some of the stabilizers flip from +1 to -1. And by basically measuring them, what you can do, at least in principle, you can actually figure out where these errors occur and then try to use this information to basically correct this type of errors. So now, I mean, like as I already mentioned, so this is an example of the CSS code where you basically, which are effectively a product of two classical codes. So, for example, like you could think about that kind of going in the z direction is like a repetition code with respect to bit flips, and then X is a repetition code with kind of with respect to. Sorry, the X is repetition code with respect to bit flips, and Z repetition code with respect to phases. And so basically, the interesting thing about these codes like surface authority codes is if we make a lattice bigger, you clearly have more checks, but you can also have more errors. And one of the kind of remarkable results of quantum error correction theory is something which is called threshold theorem, which says that if your error rate is sufficiently small, then you have like a threshold behavior. You have a phase transition where, by increasing the size of the lattice, you can actually suppress error more and more. And this is, of course, related intrinsically to this concept of code distance, again, that we've heard in the morning. And so in particular, the logical error probability in this case, is proportional to this probability of error divided this threshold error, which actually for this surface code is about 1%. And it goes into the power of d plus 1 over 2. So basically, what it really means is that you can make in this kind of system where with the code distance d, you can make errors on roughly like half of the kind of qubits going along one line, and then you can actually still correct it, And it's intrinsically related to the fact that logical operators here really correspond to z's, going all the way from left to right, or x, for example, going from up and down. But okay, so that's sort of a brief reminder of what you've heard kind of in the morning today. So, but this is also an example, showing why, implementing this error correction in practice is actually challenging. So, in particular, you need to have a lot of redundancy, right? You need to have a lot of physical qubits to encode this logical qubit. You also need to make this stabilizer measurements. So you have a lot of kind of ingredients which normally you wouldn't think about while you build a quantum computer. So, and while it is clear that eventually we would need to switch from doing quantum computation from physical to logical qubits, this example shows, why this is challenging to implement them. And in fact, up to kind of very recently, all experiments in this field were limited to doing very small number of operations on very small number of qubits, like 1 or 2 operations and 1 or 2 qubits. So I'm happy to report, and also you will see it from the lectures following mine, that it's actually now a very special time in the field, because there is now in several systems, we are now starting to go beyond this kind of small number of qubits and small number of operations. And in fact, last year there was actually a series of experiments which really sort of, changed the situation drastically. By now, this quantum error correction is really a field of experimental research. It's not just a theory anymore. So this is kind of a super high-level introduction. So maybe I pause here and ask if there are questions. So actually, I would like to make this session kind of interactive. So yeah, let me it works. So I will use this opportunity. So any questions? So far it's not, I have not, it was kind of very high level review, so maybe it's not a surprise, but nevertheless, feel free if you have any questions about either this or the previous lecture. I will try to answer. Yes.
Professor.
Yeah.
So I want to ask, so in the field of quantum information science, how confident are people with the threshold theory? I mean, why people do this believe there exists such a constant? extent of the threading error, no matter how large?
So I don't know what exactly you like specifically you're asking for. So this threshold theorem is a rigorously proven mathematical result. But of course, it's done under certain assumptions. So this assumption, for example, this 1% is an assumption under. This is done under assumption of local uncorrelated errors. And so part of the things which we are now doing experimentally is checking to what extent this error model is really correct, And for example, like if you have occasional errors which, for example, flip, half of the qubits, simultaneously, clearly this will not apply, right? Yeah. But basically, and that's kind of one of the reasons to do experiments is to check whether there are these kind of correlated errors, So that's kind of or not, This one direction. So secondly, there is some other caveat. So for example, all of his analysis assumes that these are qubits, they're just two-state system, and that's it, right? So in reality, there are like no purely two-state systems in nature. So there are always, what it means is that there are always, like every atom has a lot of levels, right? And so basically you can have, for example, things like called leakage errors. You can also, like you will see in our case, sometimes qubit gets lost, So, and these considerations technically do not apply. Yeah. So, but actually, interestingly, and this is a huge challenge, but again, it's also an opportunity because it turns out, for example, like these atom loss errors, so-called erasure errors, they actually, if you can detect them, they're very easy to connect. They're easier to correct. So in that case, the threshold can actually go up instead of going up. So I mean, these are all. So that's the reason why. I mean, this theoretical kind of work really created a fantastic foundation. But yet, it's very clear, and as you see, from hopefully my talk and also others. So as we sort of now start to really implement it practically, we often have to revisit, and things can become better, things can become worse. I mean, that's why it's an active frontier. That's why, one of the bottom lines of this lecture, this quantum error correction, of course, requires engineering, but it's not just an engineering frontier. It's also a frontier of basic research where you guys can contribute to, Yeah.
Thank you so much.
Yeah. Yeah.
So here you were saying that now we have to start thinking about error correction in logical keys.
Yeah.
Finally, we do error correction within physical keys. So you're thinking like error correct to make a logical qubit and then more error correction between those logical qubits?
So with physical qubits, you cannot really do error correction. So you can do things like error mitigation you will hear. You can sometimes try to extrapolate. If you have a noisy result, you can start to kind of extrapolate it to a less noisy result. Of course, what you also need to do, and this will never stop, you need to make your physical errors as low as possible. However, I think, at least as presently understood, it's kind of totally inconceivable that we could really reduce physical error rates to 10 to the minus 10. This is not so. And for that reason, basically this approach that, at least to some extent, uses this redundancy, uses this kind of, delocalized information, almost certainly will be a must, at least in the long run.
So if I understand correctly, like surface code, for example, that's making up a logical qubit with this error correction that we have. So were you saying that then when we have these logical qubits, we further need to do error correction within those as well?
No. So what is, let me just take a step back, again, because it's a school. So logical qubit and physical qubit are completely different animals, right? So physical qubit is a physical entity where you encode the information, which has, T1, T2, whatever, coherence time, you can do gates and so on. So logical qubits, at the same time, they exist only on paper. They exist in your imagination, right? That's kind of, and basically what you do here, you sort of uses the localized entity to encode your information. And then what you do, you operate, for example, here, you operate, if you want to flip the qubit, you apply these X operators, if you want to flip phase, you apply the Z operators. And then in addition, you have, but fundamentally, this is no longer a two-level system. Right? It has a lot of levels. And this kind of stabilizer measurement, they kind of serve to essentially check whether errors have occurred and to project it to the subspace where, it would be a happy sort of customer, So, but it's very like things which, for example, like you learned about, qubit and how to benchmark and so on. Many of them, okay, maybe it's some jumping ahead. Many of them are like not even applicable here, all right? So it's actually sometimes even like when people say, what's the fidelity of the state, with this kind of physical qubits is very clear. So with logical qubits, it's sometimes much less clear because you have all of this other information, So does it, am I answering your question?
So when you say...
I'm more like confusing you guys, but it's okay. But it's okay.
When you say we need to go to 10 to the minus 10, like
yeah,
you're
exactly.
saying we can't just do that with the surface code.
No, potentially we can. And the reason is this threshold theorem. So suppose, I give you an example, right? Suppose you have this is like, also like it depends, this threshold with respect to what, but like we will go into these details in a minute, but so it's memory, is it a memory threshold, is an operation threshold, but suppose your error per physical gate is 10 to the minus 3, right? So according to this formula, so basically it's 1/10 to the power of d plus 1 over 2, right? So if you want to have error rate, 10 to the minus 10, you need a code distance of whatever, something, around 20 or something, which, okay, it's 400 qubits per one per one logical qubit. It's a lot, but it's not, it's not out of the questions where we stand right now, right? So there is, yeah.
Sorry, just to follow up.
Yeah.
But like we were talking about how to increase the distance d,
yeah.
And there were two ways, like either you encode in more, so more physical qubits per logical qubit, or you keep concatenating.
That's right. So that is true. So in this approach, what you do in the surface code, you actually would just increase the number, just increase linear dimension. Here, distance is a linear dimension, right? You just, increase the number. So concatenation, you would just use, again, you would use more physical qubits, but then you sort of build the codes differently. So at the end, this kind of like, you actually think about that these are two distinct approaches, but actually in many kind of cases, like in high dimensions, it becomes the same. It's the same idea at the end, Yes. Yeah.
For scientific discovery, like in an error-corrected, fault-tolerant world, do you think there's still space for analog quantum simulation, or do you think everything should be basically digital at that point?
That's a very excellent question. So if there's analog simulations, or even more generally digital analog simulations, you can certainly think about error detection, where you can, for example, condition your sort of evolution on certain kind of property, and then throw away results. So it can potentially be useful. So, but how to do a really full-scale error correction with analog is currently not known. And I think the reason for that is a little bit fundamental, because as we will see, quantum mechanics, of course, fundamentally is analog, right? You have continuous rotation of the qubit from up to down. But actually, what these ideas of error correction and fault tolerance do, they turn this kind of analog dynamics into something which looks a lot more like digital, right? Because you need, when you measure stabilizers, right, you need to make a decision, whether error occurred or not. You need to make this projection. So for that reason, I think this kind of true error correction is kind of in contradiction a little bit with this analog dynamics. So, but I mean, it's an open field of research, I would say, but it's challenging for the reason I said. Yeah. Okay, so all right, with that kind of very broad introduction, so what I would like to do, I'd like to kind of give a little bit of an outline. So in these lectures, what my plan is to first give a short introduction to neutral atom quantum computing. I will tell you what one can do both in terms of analog, but also digital kind of space, and then kind of focus on like using this error detection, error correction ideas. So that's a bulk of my lectures. So if I have time, I have some extra bonus feature, which is a very recent example. I think it's on archive since last Friday, where some of these ideas are actually applied to do interesting quantum simulation kind of problem involving something which is so-called Kitaev honeycomb level and simulation of fermionic dynamics. But okay, that's, I don't promise, it depends. So I think it's better to cover less, but maybe in a little bit more detail. So, okay, so with that, let me jump onto this kind of specific focusing on these quantum processors with cold atoms. And so there are many reasons to think about cold atoms as a promising platform. One of them is that neutral atoms, cold neutral atoms, have amazing coherence properties. So, for example, like the most precise measurement instrument that humankind ever created to date is optical atomic clock, which actually now utilizes cold atoms in optical lattice. And so also it's actually relatively easy to create large number of neutral atoms. And also importantly, maybe not for these lectures, but these atoms can couple strongly to light. But at the same time, there are also problems. So first off, atoms, at least in the gaseous phase, interact only very weakly with each other. And also neutral atoms, at least historically, has been hard to control individually in large numbers. So, so to kind of like show how, to explain a little bit in simple way this challenge. So here is a picture of something which is called magneto-optical trap. So this is how all of these experiments, which I will tell you about, start. So this picture, this blob of atoms, contains about 10 million atoms, which are nearly motionless. So basically moving super slowly, very slowly. And so in principle, if we could really take these atoms and control them individually, right, you will have a lot of qubits, right? Have 10 million qubits. So basically, what it means is that the cold identical neutral atom qubits, and all of these atoms are actually identical in addition, so are essentially unlimited. So, and the real challenge is efficient classical control. So, and what we will show you how to actually control these atoms, how to convert them into quantum simulators, into quantum computers, by basically by using kind of optical techniques, by using optical tools. So to just kind of remind you, it's a one-page summary of atomic physics, what we need to know. So, sorry, it's from my class, so basically. So here is our energy level of hydrogen atoms. So, and I mean, maybe some of you guys, computer science, you never really even learn about hydrogen atom, but hydrogen atom has this kind of a bunch of levels, actually infinite number of levels. And the key is that these levels are unharmonically spaced. So what it means is that if I take a narrow band source of coherent radiation, be it a laser, microwave, or radio frequency source, then I can just individually drive one of these transitions. And there is a hierarchy of energy levels. So one of them is this electronic transition. That's something which is sometimes called Rydberg series. But each of these electronic state, then consists of several sub-levels, and they are typically characterized by things like, for example, electronic spin or nuclear spins, right? And so in each of, so basically zooming in, for example, on the ground state, electronic ground state of the hydrogen atom, you will have a few sublevels, and sublevels we'll call generally as spin states, and these are sublevels where we will typically use to encode qubits and store them for a long time. But of course, we can also, using lasers, we can excite atoms to some of these very high energy states, and actually at this point what happens is that electrons start orbiting very far away from the core, so that actually will also utilize to make atoms interact. These are the so-called Rydberg states. So so then you need to somehow grab and trap atoms individually, and for that we use a technique which is called optical tweezers. So basically these optical tweezers are essentially focused beams of light, or alternatively standing waves of light. So, and the idea is that you can actually think about each atom as a small dielectric object. And this small dielectric object will be polarizable and actually will be attracted, if you set things up correctly, to the point of highest intensity. So which basically results in the ability of focused laser beam to grab and hold one atom at a time. And so this we will use as a tool. Of course, these potentials which these focused laser beams create are not infinitely deep, so they're actually typically quite shallow. So, and for that reason, you need to basically have atoms which are sort of sub-millikelvin temperatures. However, such atoms can be produced by laser cooling, by buffing atoms in the moving atoms in the properly set up laser beams. You can actually slow the atom down such that the temperature of atoms becomes smaller than this potential trap, and then you can hold on and grab and hold on to the atom. So so this, with all of these ingredients, the way how we will build quantum systems will be the following. So what we will do is we will start with the array of these tweezers. So it's basically a bunch of beams which will focus very tightly, and we'll focus them so tightly that in each of these tweezers will be able to hold at most one atom. So actually, if there are two of them, they will not be able to fit in. They will be basically ejected, one of them or both of them sometimes. And so what it really means is that if you start with this array of these tweezers, if you try to basically load them from this magneto-optical trap, then some of these traps will be full with single atoms and some will be empty. And so this system, classically, it has a lot of entropy. So to get rid of this entropy, what we can literally do is take picture of these atoms, figure out which traps are full and which are empty. And then, once we have done it, we can then rearrange the atoms in any desired configuration. So one way of doing it is, for example, removing the empty traps and just moving the rest around. So with that, you end up with the arrays of atoms, kind of artificial crystals, if you want, which are separated by a couple of micrometers, so they're easily optically addressable. And at this point, these atoms don't talk to each other, they don't interact. It's completely classical system. So to make them interact, what we'll do, we'll excite them in these so-called Rydberg states, and then make them kind of interact and do quantum logic. So let me just kind of remind you a little bit again, for those of you maybe who are not physicists. So these Rydberg atoms are atoms where the electron orbits far away from the core, from the nucleus, and they actually have quite unusual properties. So the size of the orbit scales as a square of principal quantum numbers. So basically what it means is that for n equals 100, which realistically you can excite, the size of the orbit is a fraction of micrometer. So it's actually quite large. The conventional ground state size of the atom is like a few angstroms, So it's actually big. You change, big time this orbit. So as a result, these orbits are very easily polarizable. So if you apply electric field, then they can be easily deformed. But most importantly, if you have two atoms now sitting next to each other, then each of them will try to polarize one another, and they will interact with the interaction strength, which scales as 11th power of principal quantum number. So, and in fact, for n equals 100, it results in a van der Waal interaction strength, which is 14 orders of magnitude larger than the interaction between the ground state atoms. So, by the way, this 11th power is a very interesting kind of homework problem, So, do you guys know where it comes from? Any of you physicists? So, should we use it as a kind of, So, this 11th kind of sounds is too much, right? Is 11th power. How can it be? Where does it come from, right? Anyone has ideas how to? It's some knowledge of atomic physics, but it's very useful knowledge. So, okay, size of the atom n squared, right? So all of that originates from dipole-dipole interaction, right? So it's already n to the 4th, the dipole-dipole. But this van der Waal interaction is a square of dipole-dipole interaction, so it's n to the 8th. But there are still three powers missing. Anyone knows where it comes from? Huh? It should be more basic, kind of. So it's actually kind of useful here. Maybe return to that, to the code. We'll get back to code distances. Don't worry. But so basically, so normally dipole-dipole interaction, right? It scales like d squared over 1 over cubed, right? That's dipole-dipole. Right? And van der Waal interaction is actually a square. It's like it's second-order perturbation theory, right? It's a square of dipole-dipole interaction, but it should be, divided. Second-order perturbation theory should be divided by some kind of energy denominator. It's basically the difference between nearby spaced Rydberg levels, right? So this thing, right? So this is n to the 4th power, right? So this gives rise to n to the 8th power, right? But then there is this thing, right? And the energy, like the energy levels, they scale like for the Rydberg series, scale like 1 over n squared, and the energy difference then becomes n to the cube, right? So that's a residual, thing. So right, so basically this delta or delta omega, delta E maybe, is a derivative. It's actually n to the cube. That's where this n to the 11th comes out, right? So basically, these energy levels become more closely spaced, so that the same perturbation has a bigger effect in the second order of perturbation theory. Does it make sense? Yeah.
If you bring the two Rydbergs close together, you'll turn on a proper exchange interaction.
Yeah, so these are still, exactly, so this picture is actually, it's a good point. So basically, so this picture is really kind of valid when atoms are very far away, right? So eventually, if you start bringing them closer, this perturbation argument, breaks down, and what you end up, first you'll end up with like spaghetti of levels, which cross and anti-cross, eventually it becomes like molecular physics, and by the time this is off, and in fact, this will determine the limitation of how close you can bring the atoms, such that this kind of picture still is valid. And I will actually maybe comment on that on this slide a little bit, Yeah.
What is this 10 to the 14th times 10?
So it's just, n to the 11th is scaling, but 10 to the 14th is actual for n equals 100. It's a van der Waal interaction relative to the van der Waal interaction in the ground state atoms. It's 10 to the 14. So the ratio between van der Waal interaction for n equals 100 Rydberg states divided by the ground state interaction is 10 to the 14.
Time or space?
It's energy. It's energy for equal distance. The ratio between the energies is that.
Okay.
Right.
But in your previous slides, you also have the radius in the order of 0.5 microns.
It's a Rydberg. So this is, sorry, that's an energy difference. So this is a size of the orbit. It's actually, it's it's a little bit. I mean, I think for Equans 100 is maybe 100 nanometers, I mean, 500 is kind of extreme, I don't actually.
But that's quite impressive because that's already much larger than the transistors we have these days.
Yes. So it becomes exactly comparable. Exactly. Yes, absolutely. Yeah. I mean, But of course, you don't need to go to n equals 100. In fact, in most experiments, we go to like 50. But I mean, it shows you have a great flexibility in terms of, so, yeah. Does it make sense? Yeah.
Is there a disadvantage for having a super large n? If the n is too large?
Yeah, that's also a very excellent question. So, like based on this kind of argument, you would say, well, we should go always to higher n. In fact, there is another argument. So, if you look at radiative lifetime of these Rydberg atoms, if you go to higher n, it actually becomes longer. So based on that, you would say, well, strictly we should go to as large n as possible. But remember, however, at the same time, then when you go to very large n, this orbit becomes very, very large. And it can be easily perturbed. For example, if you have some small electric field, it would perturb this orbit. So basically, eventually, just due to imperfections and so on, like these Rydberg states just become unstable, essentially. So what it means is that you cannot, another part of the reason is that like you start getting this nearby, the spacing between levels become very small. So there is just a practical limit to how large n you can go, but it's a very interesting question. So like right now in different experiments and different systems, values of n ranging from maybe like 30 to 100, or maybe 110 or something are being explored. But and in practice, we end up often working, with maybe more like 50, But I think it's an interesting question. There is a room to optimize it, So one other reason not to go to super high n is, if you go to very high n and orbit becomes very large, then the matrix element between low n state, which you typically use to store quantum information, and high n state becomes very small. So you need a lot of laser power to drive it, and there is another practical limitation, right? Like with all of this kind of basic kind of notions, we will be using Rydberg states to kind of engineer interactions between atoms. And the way how we can use it will be based on something which is called Rydberg blockade. So what is it? The idea is basically the following. So suppose you have two atoms which are sitting far away from each other, and suppose you drive them into Rydberg states resonantly. So if they're far away from each other, then they will not interact with each other. They will just undergo independent Rabi oscillations. However, if you bring them close, then eventually these interactions will take over. And so this doubly excited state will be just shifted way out of the resonance. And so if you still try to do this resonant driving, then what will happen in the case, you will be able to excite one atom or another, but never both. And that's the essence of something which is called the Rydberg blockade. So that means that simultaneous excitation of two atoms is blocked at distances smaller than this characteristic Rydberg blockade radius. And it turns out that it's actually a unique mechanism to entangle atoms and do quantum logic in a robust way. And the reason why this is robust is because at this point, if you work in this kind of Rydberg blockade, you become insensitive to exact position of atoms or motion. So in other words, if you are strictly either far away, then it's kind of individual atom, but if you are close, it does not matter, basically, so long as you're within this blockade radius to the leading order, it does not matter how close the atoms are, right? So because you still will be able to excite one atom or another, and this doubly excited state is shifted. So in some way, at this point, this interaction between atoms becomes digital. It's either on or off. And this kind of, again, like I already mentioned that this quantum error correction and so on, it's sort of like this digital, going from analog to digital is important. So this actually is one element which you will see, which allows us to, for example, do things in a highly parallel fashion without, like, with limited calibration. This is kind of this digital aspect of the interactions. So, okay, so with all of that, so basically in what follows, I will tell you about experiments, with this neutral atom processor, which will be essentially of the following variety. So we'll start with some atoms, actually in general in 2 dimensions, which will be unsorted. And then we will kind of, make some registers from these atoms. And then what we'll do is we'll drive these atoms with laser fields and basically change the internal states, change their spin states. Sometimes excite them to the highly excited states. And then at the end, we will make another image of atoms. But in that way, here we would make an image in a state-dependent way. So that will correspond to this projective result. So it will be a result of our computation. So and all of these kind of basic ingredients, allow one to use this system, as a quantum processor, but also as a clock, as a quantum simulator. I will mention, and it's actually kind of an exploding field. I think there are over, basically 200. I stopped counting new experiments, which is being built, and actually there are at least 10 companies which already are trying to commercialize this technology, even though it's actually a relatively kind of new field. So just to kind of give you a little bit of a sense why kind of this field is exciting is because all of these basic ingredients can be used in different ways. So for example, you can, what I will show you will be using rubidium atoms, alkali atoms. But for example, there are several experiments exploring exotic atoms like alkaline earth atoms. You can also combine these techniques, these tweezers, with optical lattices, which kind of can also be used for interesting simulations. You can also, instead of atoms, use molecules, and this is another kind of direction. But so these are some of the kind of exotic recent results. So this is an array consisting of 2 different species, rubidium and cesium, in a Hannes Bernian lab. At the time was still in Chicago. And so this is an array of over 5,000 cesium atoms. This is actually from not too far from you, from Caltech group of Manuel Anders. But basically, this is a very exciting frontier because, as I said, this same kind of principle, the same system can be applied into many different directions. You can study quantum simulations, many-body dynamics, quantum computing that this talk will focus about, but also, for example, quantum metrology. And all of these things actually turns out to be, very complementary and kind of exciting. So, okay, let me pause here. Any questions? Yes.
You mentioned earlier that you reorganize the array after loading.
Yes.
For things. So do you go for 100% fill or some threshold?
So typically, of course, you want this filling to be as large as possible. So when kind of everything is like optimized, you never have 100% fills, but you can have quite high filling fraction, certainly over 99%, maybe 99.9. But of course, there will be some holes, and this could make errors, and this is something that we will discuss, Moreover, during the computation process, the atoms can get ejected from the traps. This would also correspond to another type of error, which is atom loss, which maybe we'll also discuss. You need to learn when it happens. You need to detect it and sort of correct it.
So it's like a quite fundamental question.
So in the previous slide, we discussed the potential created by the van der Waals forces. And because we're dealing with the neutral items, I think the potential is in general governed by the linear John's potential, which means Pauli exclusion for should be also involved.
Yes,
so
yes,
in
yes.
that case, why we only consider the van der Waals?
Yes, yes. So typically, in all of these cases, these atoms are separated by relatively large distances, by a couple of micrometers, such that basically all of these kind of Pauli, statistics and so on is just irrelevant, So, I mean, if, of course, you can ask what if you can pack, if you bring them close. I think it's an interesting problem, how close you can do. I mean, often you first lose this optical addressability, but, nevertheless, it is interesting, and indeed, for example, if you combine, like in Adam Kaufman's experiments here at GILA, they combine these tweezers with optical lattices. Their atoms can literally tunnel and sit on top of each other, then these things start to be relevant, Yeah. Okay, yeah.
How do
I had a
you
question before, but yeah, sorry. Yeah. Okay, yeah, go ahead.
how do you decide between using alkalis or alkaline earth atoms?
Well, it's a very good question. Like to the leading order, you can use any atom, right? But then the second order is, of course, every atom is kind of different. So a rubidium atom, alkaline atom like rubidium, has a lot of advantages because it's actually really well understood. Its properties are well understood. It can be trapped and excited with laser wavelength, which is relatively convenient. And finally, it has actually also some favorable properties in terms of Rydberg states. So this Rydberg, series is relatively universal, but there is, in each of the atom there is something which is called quantum defect. Okay, it's too much atomic physics, and it's different to every atom. It's basically, connected to like this, core electrons and how they kind of affect the outer electrons. So, and actually the reason why it matters is actually kind of related to some of the questions which was before. So we like to work in a regime where atoms are relatively far from each other, and we have like very clean isolated levels. So, but if you bring atoms closer, or if we go to higher n, then you can no longer ignore nearby levels. And what these nearby levels do, they start introducing this kind of extra level crossings and anti-crossings. So they eventually turn into the spectrum into a big spaghetti mess, basically. So you would like to work, for this reason, in a regime where you are well in a blockade, but far away from this kind of transition into spaghetti. It's actually often characterized by something which is called R star. R star is where the spaghetti starts to matter. So your distance between atoms should be smaller than blockade radius and larger than the R star. And this ratio between blockade and R star depends basically on the combination of the 6 coefficient that this kind of describes this interaction between Rydberg atoms, and this quantum defect. And actually, for example, for rubidium, it's very favorable. So that's an argument for using rubidium atoms. At the same time, there are some things which you can do with alkaline earth atoms, which you cannot do with rubidium atoms. For example, if you want to use these things for metrology, you would really like to have like optical transition, long-lived optical transition, which alkaline earth atoms have, in particular strontium has like super long transition, which is used now for atomic clocks, which rubidium does not have. So basically, at the same time, strontium and ytterbium, they require this kind of very hard to access UV wavelengths, so, and like there are these practical considerations. So basically, at the end, depending on what you want to do, there is kind of an optimal, species of atom, And now, for example, you can also use multiple species. You can use one for one purpose and another for another, and that's what partially this drives this experiments. Yeah.
I think you mentioned in a previous slide that one of the advantages of the neutral atom is the long coherence. Right?
Yeah.
But if someday we have QEC and we can do everything fault tolerantly, is that still an important
Yes. So I would say the answer is resoundly yes, because as I already indicated, this QEC has things like threshold. So and the lower is your physical error rate, the less error correction you would need to do. So for example, in this example which we talked about, of this surface code, right? If you are 2 orders of magnitude below threshold, all of a sudden you need, way less atoms or way less redundancy to achieve the desired error rates. So basically, and in particular in these cases for neutral atoms, and it will become clear, so we almost never have to correct memory errors. So our memories can be very long, so it can be, without working hard, they can be easily seconds, and if you, work hard, they can be maybe, hours and days, So, the only errors we need to correct is errors in quantum operations. And that actually is, that simplifies, a lot of kind of designs. I mean, it's still a very hard problem to do error correction, but it makes it much, much easier. So basically, the rule is if you can improve your memory times, if you can improve your gate errors, as much as possible, you should do it, and this effort will never stop. But the fact that you don't need to worry about memory errors is a huge advantage.
Because I was thinking that if other platforms, although they have less coherent time, but if the operation can be done faster and the QEC cycles can be faster, then maybe it's not a problem.
Well, okay. I mean, yes, but then they, you have to look at. Basically the error per cycle, what matters, and where it comes from matters, right? And so, it is true that what you will kind of see is that, let's say, compared to superconducting qubits, the speed of our quantum operations is actually comparable, but the cycle of error correction will generally be slower because you'll see why, because we actually like to move atoms around and so on. But in terms of this question of what's a relevant figure of merit, it turns out the answer to this question is very subtle. So it turns out, for example, it depends on how many rounds of error correction you need to make per cycle. And hopefully I will come to that, But so with all of that, still, if you can reduce the error per cycle and make certain type of error negligible, you should absolutely do that, But it's error per cycle, of course, which matters. And the memory error per cycle here can be really made negligible. Yeah.
I just had a follow-up question from something that someone asked previously. I was wondering if mixed systems or hybrid systems with different atoms was possible, tweezers, set of tweezers with one set of atoms and a set with other, use them for whatever they're specifically good for, something like hybrid like that. Is that interesting?
Yes. So it's exactly. So first, the way how it's done here is you basically literally use different colors of light, and basically, you make it such that, one color of light does not affect another, right, atom. And, potentially it can be used for different purposes. For example, what you could do, you could just measure one type of atom without affecting the other atom. Or you can do 2 different types of atoms. For example, if you want to combine quantum computer and clock, you can use one type of atom as a clock and another one to do a computation. So I think, it really opens the door to many cool possibilities. But again, depending, but it also adds complexity, right? Depending on what you want to do in life, this might or might not be the right thing to do. But it really creates an additional dimension where you can really be creative and explore things. Yeah.
Since we are using Rydberg state and we need to set the atom at a very high energy level, I'm just thinking that if the electron is sufficiently far away from nuclei, will it eventually lose it and become an ion or something?
That's right. So that can happen. So, but of course, to ionize it, you need to typically kind of there's a threshold, right? You need to push the atom kind of beyond this threshold. So typically, when you use atom to laser to excite into the Rydberg state, use certain color of light, which actually just puts you in exactly the right state, But of course, if you have some other imperfections, electric field or maybe radio frequency fields around, they can actually ionize atom, and this could be an error. Right? Yeah.
What is the motivation for using molecular arrays? I would imagine they'd have a shorter coherence time.
Well, the molecular arrays are kind of interesting. So in molecular arrays, you can actually try to entangle atoms without exciting them to Rydberg states ever. Right? Because even in the ground, like even rotational states, they have dipole. I mean, for the polar molecules, they have dipole. So you can just use this dipolar interaction to entangle. And people indeed have done it. Just literally last year, they created entanglement and did even quantum gate errors. The problem is, of course, like the dipole moment in this for polar molecule is actually quite small. So these operations are kind of slower. Of course, their lifetimes in principle are larger, but there are opportunities here, but there are also limitations, basically. Yeah. So, yeah.
Can you also make 3D arrays out of neutral atoms, or is that only 2D?
Yes, it's also a truly excellent question. So, in principle, you can make 3D arrays. And for some applications, this can be actually useful. For example, you can pack a lot more atoms all of a sudden. One limitation, however, is that you will lose some degree of parallelism. So in this, we have 2D arrays, we can control all of the atoms at once, independently. So you have 3D, so you can maybe control them layer by layer, but these are all kind of interesting future directions. Yeah. Yeah.
Do you see any of these materials as scalable, something we can push all our chips on, or do you think material identification is should be the #1 priority?
So, let me just, maybe explain. So here, in all of these pictures, these are all pictures of single individual atoms which are sitting suspended in a vacuum chamber. So there is no material problem. They're all identical, God-given atoms. They're you cannot have better qubits than this, right? So there's the material choice is a choice of atom, right? So, and the only thing you need to do, you need to control these things, and that's where these optical controls come. So, so it basically it just pushes away this materials problem. Of course, you can correctly ask, and we'll talk about it towards the end, how scalable these things, is already pointing out. So now we can sort of, manipulate arrays containing, around 1,000 qubits, There is certainly a very clear path to tens of thousands, probably 200. So, can you scale it to tens of millions? One might need to have new ideas at this point, But, I would say, at least at this present point in time, it's certainly one of the most scalable systems as it currently stands, Yes, Jay. Yeah.
Going back to the starting point, you have all the atoms in the mod. Sounds like by name, you need some magnetic field to hold them. So how do you use that? These are neutral.
Yeah. So yes. So mod indeed has in this mod indeed you need magnetic fields, and you need also often gradients of magnetic fields. To create these atoms. So what we typically do, have done up to now, is we would create these atoms in the mod, and we would turn the mod on, and then we would actually start building our processor, trapping atoms in a tweezer, and so on. So we typically, even when we operate this tweezer array, we typically work in a finite field. It's small magnetic field, maybe like 10 Gauss. It's larger than Earth field, but not much larger, to just resolve different individual levels. But of course, one of the questions maybe is in the long run, you would not like to do a quantum computation with error correction, which might last for a long time, So you might not have a luxury to like building a mod, and sort of refilling these atoms. So if we have time at the end, I will tell you about a new way how to do these experiments. And basically the idea is that this atom preparation can be just in separate zone, which can totally, the fresh atoms are brought to the processing zone. So this is a kind of a new way how to do it, which would enable long computation. So this mod can be completely separated from that.
But you need a magnetic field to hold the atoms in the mod, or how do you?
You need magnetic. So the mod. Okay, it's maybe a separate lecture. You need magnetic field grade. Yeah, you need magnetic fields to create a mod. You actually also need magnetic fields to build arrays, but they're kind of a little bit different types of configurations. So that's why you would like to actually decouple. I mean, right now in most of the experiments today, what you do, you create a mod and you switch all of the mod sort of infrastructure, and then you just do, things with the build array. But in practice, you need, like in the future, or actually in very near future, you need to do these things in parallel. So you need to basically bring fresh atoms and refill the arrays. And, we can maybe talk a little bit about that. Okay, so let me maybe proceed a little bit. And so, talk a little bit about sort of practical aspects. As we already kind of discussed here, there is this issue of choice of atom. So it could be either alkali atom like hydrogen-like, or this alkaline earth. So this alkaline earth atoms like strontium or ytterbium, basically it introduces extra complexity, but it actually creates maybe new opportunities. But even within a given atom, you can also have a lot of opportunities in terms of how you encode a qubit. And so, for example, like in some of the early experiments, we utilized this ground Rydberg encoding. So we would encode a qubit in a superposition of ground and Rydberg state, which in some way is easiest, requires least kind of infrastructure. But but of course, in the long run, it's probably not the most ideal. So ideally, you would like to store qubits in these long-lived hyperfine states, and then just only when needed excite them into Rydberg states with the short pulse. And all of this, depending on now what you want to do, you can actually choose, right? And often it just involves switching a laser or adding a pair of lasers and things like this. So here is an example, like in a kind of ground Rydberg kind of manifold, how you can use blockade to entangle atoms. And so here you can just start with the pair of atoms sitting next to each other and excite them in a Rydberg state. So for this rubidium atom, actually you do it with 2 colors of light. It's a 2-photon excitation, but it's kind of technical detail. And the idea is basically the following. So if you are kind of on resonance to this Rydberg state, right, you can, under condition of blockade, excite one Rydberg atom or the other, but never both. So this kind of double excited state is completely shifted from resonance. And actually, if you do it in this configuration, you can excite one atom into Rydberg states, but you don't know which of the 2 atoms you excited. So you actually create an entangled state for this reason. And actually, you can verify it by looking, for example, that's a probability of both atoms being in a ground state. The probability of one atom excited and the probability of both atoms excited is basically noise, is 0. And so you can then also verify that this superposition has well-defined phase. You can basically, by applying a phase shift to one atom and kind of making them like, the superposition kind of precess. And so basically this way you can really reconstruct, for example, a density matrix for these 2 atom states. And, this is actually some of the early experiments already. So it's almost 7 years ago. And basically they show that you can entangle them with reasonably high fidelity. At the time it was 97%. By now it's actually approaching 3 nines. And you can do it very quickly within actually tens of nanoseconds. So basically, okay, that's how you can build an entangled state. You can also think about using this system as a kind of programmable simulator of spin models. And the simplest idea is that you can just start with a line of atoms. And then there's a Hamiltonian which describes these atoms. And this Hamiltonian has this rabbit term, which actually kind of acts as a transversal magnetic field effectively. Has this detuning term, which actually is like magnetic field pointing in the z direction, and an interaction term. And this kind of Ising type model, you can actually basically calculate here the ground state phase diagram. This can be quantified by two kind of parameters. One is this detuning, delta, the laser detuning, and another one is interaction range. And basically, if there is no interaction, if interaction is 0, then depending on the sign of the detuning, you either want atoms to be all atoms in the ground state, for example, like this, or all atoms in the excited state. But of course, this kind of all atoms excited is incompatible with Rydberg blockade. So for example, if you have nearest Rydberg blockade, then at most you can excite half of the atoms, every other atom. If you extend the size of blockade, you can only excite every third atom and kind of et cetera, et cetera. And so basically, you can easily explore this phase diagram by preparing all atoms in the ground state and sweeping detuning from left to right. And if you do it, you can immediately see, for example, how this order builds up. So here there is this up-down order, which builds up. Every other atom is excited. So here is up, down, down, up, and so on. And basically, what you see also, if you see these snapshots, as you change this detuning, you see how this state with all atoms in the ground state turns into this kind of ordered state. And in between, there is actually a quantum phase transition. There is quantum fluctuations drive you from one state to another. So you can really study this kind of physics. It really literally implements these ideas of Feynman from 40 years ago, right? So to kind of study this kind of quantum, simulation systems. So okay, so the modern version of this approach utilizes a two-dimensional array. And this two-dimensional array is powered by the device called special light modulator. This actually is the same type of device which is used in this slide projector. So it's basically, essentially it's a computer-generated hologram, which you can basically program to deflect the light in a certain way. And if you do it correctly, so what you can do, you can form this kind of arrays of two-dimensional kind of laser spots, which you project in the vacuum chamber. Basically, creates this array of optical traps, thousands, actually tens of thousands by now. And so the only disadvantage here is that this special light modulator is relatively slow. So to move atoms around, we actually utilize a second channel, and this channel consists from different types of optical devices called acoustoptic deflectors. So acoustoptic deflectors basically convert radio frequency waves through the sound. They take one laser beam, and basically the radio frequency waves deflect this laser beam in different directions. And here, by using two of them, you can basically move rows and columns of atoms independently. And all of that can be, of course, computer controlled. And so this is kind of, for example, so very old movie, how we can actually rearrange. At the time, we were very proud that we can actually rearrange atoms, about 600 traps, maybe 300 atoms, how we can create nearly defect-free arrays. I should put a date on it. I think it's from 2019, so. But, basically, by now, as I said, this filling can be actually is reaching 3 nines fidelity. And you can, of course, create different types of configurations, including this kind of arbitrary patterns, which you can program and just, press a button, and here they come. And in this kind of approach, you can also extend this analog quantum simulation modality. So, for example, you can start with this square lattice array and program interactions such that only nearest neighbor atoms are blockaded. And if you, for example, do the same trick which I described, you just change the tuning from negative to positive, you can create this kind of picture where every other atom is excited. And this actually is ordered pattern, is anti-ferromagnetic pattern. And you can study it either kind of like as a many-body system, looking at the correlation function, or you can study it microscopically. And this is, for example, like you basically can make a statistics of these patterns which emerge. So these perfectly ordered patterns don't always appear. In fact, they appear only exponentially small number of times, but still the probability of this pattern is actually stands out, is actually largest from any other microscopic state, and it's kind of actually decreases with array size, as it kind of should. But you can also not only study statics, you can study dynamics, you can study correlation growth, and, for example, extract these are the so-called critical exponents. So actually, the transition from this state to this state is a quantum phase transition. It's driven by quantum fluctuation, and it's characterized by various types of kind of many-body correlators and by these critical exponents. And this is a kind of a thing which actually we have already been exploring for over 5 years, but it actually remains an active subject of exploration. So, for example, this week in Nature, there is a paper where we actually explore the so-called coarsening dynamics. We study how these correlations emerge, how they grow, and it's actually still a kind of cutting edge of science. So, okay, so but so with all of these tools, over the last 5 years or so, we have had a lot of fun. So we have explored these different phases and their dynamics. We pushed the system away from equilibrium, and actually there is and discovered something which is by now called quantum many-body scars. Is actually a non-equilibrium effect which was not known previous to these experiments. So we actually created some baby versions of topological qubits. Studied also optimization. So all of these approaches involve analog dynamics, and actually one of these analog machines is available for nearly 2 years now on a cloud from our startup company, Quantum Computing, and actually some really cool scientific results, have been obtained from this system. But what I would like to do today is I would like to focus on this kind of digital processing and kind of involving this quantum error correction frontier, but maybe it's also a good time now to stop for questions. Yeah. Okay. Yeah. You guys. Yes. Yeah.
So I guess there's many excited states in the neutral atom.
Yeah.
I was wondering if we can do, if it's like a qubit. I was wondering if we can do like monolithic qubit. So
Yes. Yeah.
this is A coding and the coding.
Yeah. Okay. So I mean, first off, you certainly can do qubits, both on the ground state. You have many states, but also in the excited states, you can excite many of them. So both are options. I mean, there are some kind of technical issues, for example, like in terms of how sensitive these lower states to things like magnetic fields. There are 2 states which are least sensitive, which we use. So the other ones are more sensitive, but it's an option, Likewise, this, in principle, you have almost infinite number of excited states. And actually, like some time ago, like nearly 10 years ago, there were papers, about, like, for example, bosonic codes. I mean, how practical they are, to be honest, I'm not completely sure, but absolutely one can explore these things. And I think people are still thinking about them. Yeah. So you can utilize this kind of internal complexity to do that. Yeah.
I wonder, because maybe the states are unstable, like the higher order states, but could we do further cooling yet?
No, so the lower for example, like even rubidium atoms has 8 hyperfine states.
Okay.
So I mean they are super stable. they're a little bit more subject to dephasing, but I mean, these are all principal problems which can be resolved, right? So, I mean, yeah, in principle, and, yeah. And there are different ways to do bosonic codes, so, I mean, there has been some thinking. I mean, experimentally, I must say, they haven't been yet implemented, but, this, yeah, it's an interesting avenue, yeah.
So 2 questions. The first question on behalf of non-physicists.
Yeah.
So there's this word order used a lot. I wonder just what does that mean?
I see. So this refers, and there's a kind of maybe a small interlude. So this refers to something which is called quantum phase transition. So phase transition, as you know, is when, like, for example, you take liquid and freeze it, the crystal emerges. So crystal breaks special, symmetry, right? Translational symmetry, and in this crystal, you could think about like molecules or atoms are ordered, right? So what we study here is like a quantum version of this phase transition. So in this liquid water phase transition, this transition is driven by thermal fluctuations, but in these cases, you basically start with system at 0 temperature, and to a leading order, you don't change the temperature of the system; it's still at 0 temperature. But what you do, you basically change the Hamiltonian parameter. And at some point, these quantum fluctuations become like dominant, such that basically the system wants to crystallize. That's what we're exploring. So this quantum phase transition is like the super exciting frontier of many body physics. And these systems naturally allow you to study these kind of things. Yeah.
And there were also like Z2, Z3, Z4.
Yes. These are two.
Basically, you can.
Yeah, there are different types of like order, right? So, I mean, like they're actually, in this case, in 1D is kind of very simple. Oh, sorry. So so these are like, they're actually exceptionally simple. You can understand this from this kind of blockade perspective. So this is like, so Z2, it makes, what it refers to, it breaks Z2 symmetry. So every other atom is excited. So Z3 like Z3 symmetry, right? Every third atom is excited, and this is Z4. So that's referring. They're actually, classically, it's very easy to understand the states, but for example, transitions to all of these states, are extremely non-trivial. In fact, has not been, like some of them before this work, which now is a few years old, have not even been well understood, And in 2 dimensions, depending on the type of lattice you work with, you can have all sorts of different ordering patterns. So it's actually, there's a full zoom of them, and this is what one can explore.
So actually, second question is, there are 2 lasers for the Rydberg gate.
Yes. But it sort of does not matter, because each of them doesn't really have much effect on atoms, but together they just have exact energy to put you in the right state.
Oh. So it's
the so-called 2 photon. It's a sum, exactly.
Oh, okay.
Yes. Yeah.
Misha, in your next slides, you have both W state and the D state. How do you know which state they are in? Both are
so basically, which state you excite here depends fundamentally on like laser phases. But the way how we actually can measure this is, which state, and we can verify superposition is, so if we excite them into this W state, if we de-excite, these lasers couple to only W state, right? Not to D. D is like dark state. And so to actually, but the way how we verify that we really create a pure state and not some kind of mixture is we change the frequency of one of these atoms. We apply a laser beam which creates a small frequency shift. And what it does, basically changes its phase. One atom now processes a different frequency, and it kind of goes into this other state. Then if you try to de-excite, all of a sudden you don't see anything. Right? But if you wait for a little bit longer time, then it comes back and you can de-excite. So that's how you can basically reconstruct this density matrix here. Does it make sense?
It's not an energy split, it's a symmetry forbidden transition to
Yeah, exactly. There is no energy, exactly. So it's just, the laser phases, the given laser phase, you can excite one and not the other, right? Yeah.
Sorry, for the physics applications, if you can already do all those amazing stuff without error correction, what can error correction allow us to do that we can't do right now for physics?
Yeah, so, it is a very good question. But so, for example, like if you look at this result, like at the result of what's the probability to get like a perfect pattern, right? So this okay, I should put some caveats. The pattern, this perfect ordering, might be imperfect for different reasons. So one of them is actually quantum fluctuations. Is that something you can study? But suppose you move deep into ordered state, so then this state should really occur with unit probability. But in practice, this is not. Sorry, now I need to wait until. So in practice, it's not the case. And so what it really means is that during these evolutions, errors happen. Right? Some atoms can decohere, depolarize. Atoms can be lost, right? And fundamentally, this limits effective circuit depth of your evolution, right? So, and now the question is, depending on what problems you solve, is the circuit depth enough or not enough? So actually, as we speak right now, the analog evolution allows for longer circuit depth, certainly in our system, but even in superconducting platforms, or actually this paper about coarsening, that I mentioned, it actually will come on the same issue as a kind of a paper from Google, which is on archive, where they use analog. They for the first time do like analog simulations. And so the analog simulations allow effectively for longer, circuit depth than the digital at the moment. So, but what you see is that if you, for example, scale array size, you see that this probability, right, goes down, right? And now, like if for some applications, for these many body applications, it might be okay. You can still explore things at least qualitatively. But if you, for example, want to solve a problem of determining certain energy, super precisely, then it will not be sufficient, And basically, and what it really means that at this point you need to somehow do error correction, And for analog systems right now it's really unclear if you can do it or not and how, right? So basically, by doing digital, for example, for quantum simulations, if you start doing digital simulations, to begin with, you actually incur some overhead, but the hope is that eventually, this will be more than compensated by, for example, ability to, to do like error correction, but also with if you have a universal digital kind of system, you can also measure different things, which you cannot always measure with analog settings. So there are differences. All right, so should we make a break here? Okay.
Coffee break, reconvene at 4 o'clock.